as folks are settling in, do also want to acknowledge that particularly today I'm joining from UW Tacoma's campus. And so that means I'm on the Coast Salish lands, particularly of the Puyallup tribe of Indians. And as we're thinking about research from students, I'm reminded of an idea that Mike Brett, a colleague, has advocated for, which is the idea that UW is in a unique position to offer free tuition to members of Washington state tribes. And so just going to put that idea back out into the ethos as we think about not just words, but action when it comes to our relationship and collaborations with the tribes. A lot of really great content. So with that, I am going to hand things over to Joel to kind of set the stage.
Thank you, Marielle. Good morning, everyone. My name is Joel Baker. I'm the director of the Puget Sound Institute at UW, and we are very pleased that so many of you are able to join us to hear these very interesting talks. The Puget Sound Institute is really built around three main ideas. The first of which is, and it's disappointing I have to say this in the year 2025, but one of our ideas is facts matter and science matters. So let's build a common understanding of the underlying processes of the Salish Sea so that we're advising the policymakers as best as we can. Second idea is let's show our work. Let's have the trust and confidence in each other to share preliminary findings and crazy ideas and embrace constructive criticism. That's how science works the best, right? So then the third thing we think about is really thinking about the Puget Sound on the ecosystem scale and over the time periods of decades. This is a really large, complicated system. But Puget Sound Institute, we really try to own this idea of thinking at a large scale and over decades, and I know many of you do as well. So today we're excited to host the latest session in our Science of Puget Sound Water Quality series. Many of you have participated in the earlier sessions that are shown up on the screen here. These are all available on our website if you want to go back and see these the earlier presentations on the Science of Puget Sound Water Quality. And with that, I'd like to turn it over to my UW colleague, Parker McCready, who will introduce our speakers. Parker.
Hi, I'm Parker McCready from the UW School of Oceanography. And just giving a little bit of background of what activities are going on in terms of Puget Sound research at the University of Washington. A couple of recent papers that are exciting. One, my former student, Elizabeth Brazil, just published a paper in JGR Oceans about where the water that comes into Puget Sound and the estuarine exchange flow comes from, and pretty exciting results. Another one by Elstrom et al. About nitrate coming from rivers. And then we have a number of students co-advised by myself and Alex Horner-Devine and Mike Brett. And two of them you'll be meeting in depth today, so I'll wait to introduce them until the next slide. But my postdoc, Jilian Xiong, has been working a lot in the LiveOcean modeling system, and especially on budgets, but also lots of other things. eDNA from dolphins in Hood Canal, marine carbon dioxide removal. We have a number of different ways in which we explore the functioning and potential uses of the Puget Sound and Salish Sea and Pacific Northwest marine waters in our group. My other student, Erin Broach, is just about to finish her PhD next month. Go, Erin. And she's really trying to understand how the exchange flow works in Puget Sound. A lot of what we do in our group is sort of this combination of estuarine physics and how it shapes biogeochemistry of all sorts of things related to hypoxia, as you'll hear here, but also harmful algae blooms, ocean acidification, and other things. Then the UW Puget Sound Institute, I assume, Joel, you just introduced that, so I don't have to do that again here. But I do want to highlight the next workshop, which you saw at the bottom of that slide, with Tim Messington and Stefano Mazzilli, and talking more about oxygen supply and demand. That'll be exciting. Okay, next. So our speakers today are UW graduate students, Dakota Mascarenas and Aurora Leeson. They are formerly in the Civil and Environmental Engineering unit, and co-advised by me and Alex Horner-Devine. But you should also know that I'm retiring soon, so my postdoc, Jilian Xiong, will be taking over as co-advisor. And they both came into the program about 2 years ago. Dakota, as you'll see, has been, well, a little background. She has a previous degree from Stanford, and then Aurora has a previous degree from Harvey Mudd down in Southern California. So both outstanding students, and you'll see that they're taking very different approaches. They're both funded by a project that is studying the effects of sewage on, or treated sewage in Puget Sound in relation to hypoxia. But we're really taking a very kind of, digging into the basic science, like what can we say is actually happening with hypoxia, and can we say why? Before getting into the details of how changes in sewage treatment might alter that. So I'll let them talk more about that. Okay, next. Just a little bit about hypoxia. That's oxygen concentrations in the water that are low enough to be negatively affect organisms below 2 milligrams per liter is a typical number. And in general, it's affected by the interaction of biology and physics. So up in the, what we call the euphotic zone, where the sun gets in the surface water, say the top 10 meters in Puget Sound, then you can have photosynthesis, especially if you have sunlight, and nitrate is the main limiting nutrient, and then phytoplankton grow, and that actually increases oxygen. Also, exchange with the atmosphere always tends to increase oxygen in the water as well, because there's lots of oxygen in air. But then all that organic matter put into the phytoplankton, those eventually die and sink as particles, and they sink through the stratified waters to the bottom, and anywhere below the euphotic zone, they start to be degraded by bacteria and sort of eaten up, just like we eat things. And when they do, they use up oxygen. And so preferentially, oxygen is removed from the bottom water. And that is a pattern, that's a naturally occurring pattern that we see throughout Puget Sound, but especially it gets quite extreme in Hood Canal in the late summer. And, but lots of other places around the world. But it also can be a process that is made worse if humans put more nutrients into the surface water. And that's what's being explored here in part. Next slide. Then this changes in oxygen are also part of the larger story of global climate change. When water gets warmer, that it's less able to absorb oxygen from the atmosphere. And so you get less oxygen coming in from the atmosphere, but also organisms tend to have a greater oxygen demand when it's warmer. And so it's kind of a double whammy for them when things get warmer. And this is something that's been explored in global climate simulations and also with observations. And without further ado, let's get on with our speakers.
Thank you, Parker. Dakota, I will give you the reins.
All right. Let me share the right thing. Okay, everyone can see?
Looks
awesome.
great.
Well, thank you everyone for that excellent introduction. I'm Dakota Mascarenas, and I'm excited to share with you the work that I've been doing for the last 1.5 to 2 years. And I want to start off by just saying that This is not just me in a silo working on this, so thank you to my research group for all the support, as well as all of our collaborators that aren't necessarily a part of UW, even people that are willing to answer cold emails from a random graduate student about their data methods, and everyone who's been a part of this community to help this research has been very important. So thank you so much for all of those who have helped so far, and then also for everyone with your diverse expertise here today to help make this work more complete. So I will be talking about 100 years of Puget Sound dissolved oxygen, but I won't just be talking about oxygen. I'll also discuss temperature and salinity, because these properties are often concurrently measured, and they also tell us something about the system as a whole, how the system might change over the last 100 years, and they might also impact dissolved oxygen as well, which I'll get to later in the talk. So my agenda is pretty straightforward. I'll start with my context and background for this work, and then I'll spend a lot of time actually on data and analysis. That tends to be something that I think people can occasionally glaze over, but has been a lot of the work that I've done. And so I want to share with you the processes that we've gone through to make sure our analyses are meaningful and impactful. The results that I will share are long-term trends, and then I will get to conclusions and future work. Okay, so to set kind of the baseline level of context, as Joel and Parker have already started to discuss, our science mission with this project is to bolster our scientific understanding of the processes impacting dissolved oxygen in Puget Sound. For my part, I analyze historical and modern observational and monitoring data to understand long-term trends in water properties. By doing this, I hope to help provide the necessary understanding to further investigate the role of land-based nutrients in Puget Sound dissolved oxygen. So in this presentation, I actually won't talk about nutrients, but I will talk about the systems impacting dissolved oxygen. So broadly, I will want to answer this question: is dissolved oxygen changing in Puget Sound? If so, why? And I'll do that in two parts. The first question, or the first sub-question, is: do temperature, salinity, and DO show trends over time, specifically over the last 100 years? And then what mechanisms might explain these century scale trends? Before I delve into that, I'm not the first person to ask these questions or to look at observational data to do so. And so what I want to investigate in this slide in a non-exhaustive way is what we have learned from observational data so far. And so this is specifically focusing on papers that have discussed monitoring data and how that might inform trends and mechanisms for those trends. So the first question, as related to my first sub-question, is: do we observe trends in temperature, salinity, or DO? And this is a list that kind of goes over some different eras, but also some different findings that have come out of the literature. But in the 70s and 80s, some legends in the field conducted very similar analyses to what I'm doing today and what I'll show you, and were not able to identify trends over time. They were using data that started in the 30s, and that's the same data I'll use today. But in their analysis in the 70s and 80s, they were not able to identify trends over time in that period. In Hood Canal, Jan Newton et al. Did identify that in the 1990s and early 2000s, it's statistically significantly higher dissolved oxygen than it was in the 30s and 60s. And then in the Straits of Juan de Fuca and Strait of Georgia, secular warming trends have been identified. So warming trends that are persistent over, on a century scale. And then the next question that I've tried to parse from the literature in this brief slide review is what factors might be linked to those variations. And so what we found is that there is linkage on an interannual to decadal scale on Puget Sound water quality properties to the Aleutian low, to El Nino, to coastal upwelling, essentially offshore processes that have interannual or decadal scale oscillation that might impact properties that we observed in Puget Sound. Recent work also has identified that there might be more correlation between local environmental factors, so local temperature, local river flow, et cetera, with temperature and salinity than with offshore forcing. So we have both this local and offshore variability that might play in, but this is sort of what we've been able to glean from observational data so far. So now here we are 100 years, we have about 100 years of data. And so what we found is that there's this unique opportunity to use that data to understand these trends over time using the longest time series that we can, and then also identify century scale mechanisms for change. So now we'll get into the weeds of my first question. And I'll start with the data and the analysis that I've used to answer it. So the first question that I will pose and then answer is, why do we need 100 years of data? So I've been talking about that a lot. It's a lot of data. Well, we need that to be able to understand a few things. So first of all, in a system like Puget Sound, we know that variation occurs on shorter timescales. And so this is an example this is more of a conceptual example, but it is using real data from the Department of Ecology monitoring. This is a monthly average of all Puget Sound sampling stations between 35 and 105 meters deep. So it's an average of a fair few on a fair few axes. But what we can see is in this time series of DO from 2010 to 2018, we have seasonal variation at the very least. So we have an oscillation that occurs on a seasonal time scale. But if we wanted to know, what's the trend over the last 10 years, we could fit a trend line, as has been done in this red line, and you would see that we can smooth out that oscillation and understand the change over a longer period of time. But variation doesn't occur just on seasonal timescales. It can also occur on timescales as long as decadal variation. And so if you zoom out that time series and start in 1999 and go to 2018 in this case, what we see is we definitely have that seasonal oscillation, but there also is, potentially, if you look at this time series, there might be a bit of decadal oscillation as well. And so in order to understand, truly have things changed in the last 100 years, we need the longest possible time series to understand those trends. So I have spent the last couple of years wrangling 100 years of data, and imagine you're a grad student and you're like, we have all this data, you don't even have to collect it yourself, we just have to look at it and find meaning. And they're like, that's easy, that's no problem. That's a lot of data to deal with. It turns out that it's not as easy as I thought it would be to actually derive meaningful trends, because there's a lot of variation over time in the data set itself. And so I'll go through kind of how I've sought to control potential areas of bias that might be introduced. So variation in sampling techniques, location, depth, and frequency could introduce bias. And so we have to control for those variations over time. This plot is a plot of every single location of a CTD or bottle cast, so like a shipboard cast that we're using in this analysis, and over the entire time series that I have. And I have several different data sources that are informing this plot and also the analysis. And so obviously what we can see kind of on first pass of this plot is there's the different densities that different agencies maybe preferentially sample different locations. But I'm going to talk first about the sampling techniques over time. And so we kind of have a good understanding. I think a lot of us in this virtual room know how modern sampling techniques are done. But what I had to learn as a graduate student is like, how is it done in the 30s and the 40s and so on? And so the really valuable historical data set that we have to use that gives us our almost century worth of resolution is this Collias data set, which a lot of you have probably worked with, but it spans from 1932 to 1975, and it was compiled and collected by Dr. Eugene Collias at University of Washington. He compiled some earlier work and then also collected his own data as well. And so what was good for me to find and also learn about this whole process is that even in the 30s through the 70s, bottle samples were, or to understand oxygen measurements, bottle samples were taken and then Winkler titrations were used to get that measurement. And what that kind of tells me about the variation in the sampling set is because modern bottle samples also use Winkler titrations and CTDs are calibrated against Winkler titrations, we assume that there is minimal bias due to laboratory techniques in this set. So that's a really helpful thing that at the very least we can count on that historically things were done to the best standard that they could have been done. And modern sampling is not too much different. And so this is good in order to understand and control for that bias. So I've added a few more things to this plot. Again, we're still colored by agency, but this is where I'll kind of talk about spatial variation and also temporal variation and how that can bias the data set. And so in this case, I've already shown you this plot with all the locations. In 2D space, we have areas that might be sampled more frequently than others. So if we took an aggregate of all of Puget Sound, we might have years where we're sampling just near Seattle or just in Hood Canal. And we know that those have different water quality properties and could thus bias the trends that we see. This top right plot is a time series of the average cast depth over time. And what we see is that partially based on the spatial variation, but also due to potentially sampling technique or sampling intent, the depth of the casts go to over time can vary. And that can also introduce bias. So not only do we have 2D spatial variation, but we also have 3D spatial variation. We also have differences in depth that could influence the sampling that we compare over time. And then this bottom plot is a time series of the frequency, how many casts were conducted in a specific year. And what we can see in this plot is that there's a lot of variation there too. So there's a lot of differences in how many samples were taken. And again, if we're not careful with the data, you can introduce bias by assuming that potentially you have a more even distribution of casts in time. So we have to control for that variation. So what data should I use to analyze and understand trends? So what we did is with our 12,000 plus CTD and bottle casts is we selected sites for analysis that met specific criteria. And some of them are fairly obvious, but we wanted to select sites that were consistent. We have, a lot of casts taken in one specific location in Puget Sound over time, so we could understand the trend at that site specifically. We also controlled for consistent sampling depth, and I'll get into kind of more what that means. And then I also we're constrained, if we had 200 years of data, that would be great. But because we only have about 100, we wanted to ensure that all the sites that we're using have at least 6 decades of data to control for decadal variation. And so we also consider trends for this presentation when and where hypoxic risk is highest. And that's at the bottom of water columns and during late summer and early fall, which Parker mentioned in the introduction. And so I'm going to show you an example of kind of that data wrangling at one of the sites that I'll talk about in far more depth. But this site is Point Jefferson. It's near the deepest part of Puget Sound. And it's also one of our most complete time series. It's a long time series, been sampled for almost 100 years. And that's really exciting to have that data available. And so among all these casts, we've selected this site where the cast locations are fairly cohesive. And then we've also considered the depth over time. And so this plot here is a time series of the annual Puget Sound average cast depth in gray, but also the red indicates the Point Jefferson cast depths themselves. So how individual casts at Point Jefferson, how deep did they get? And so what we wanted to make sure of is that we had a window where the cast depths, especially toward the bottom of the water column, were consistent enough over time that we could group them and average them and compare them over time. So in this case, Point Jefferson, we defined a window that was approximately 20% of the water column depth at this site. And beneath that depth, we were able to have consistent casts over time and compare the results throughout the time series. And then finally, this last plot is just showing that we have 60 years of available data to use and more at Point Jefferson. So I applied that same criteria to as much of the data set as I could, or as much as we could within the data set, and we were able to find 5 sites that met that criteria. And so I kind of grouped them into 2 groups, as you can see, based on color. And the first 2 sites are Point Jefferson, which I've already talked about, and near Seattle. And these are what I'll call my main basin sites. They're in the central, deepest portion of Main Basin. Main Basin is also, it's connected to all these subbasins. And so a lot of the water that then enters subbasins must flow through Main Basin in some capacity. And so it is really connected and central in terms of the water quality properties in Puget Sound. These 3 sites in blue are what I'll call my subbasin sites, and kind of conveniently, with the data I was able to find within the data set that we have, sites within each of the subbasins. So we have Saratoga Passage up in Whidbey Basin. We have Lynch Cove in Hood Canal, and then Carr Inlet in South Sound. And these sites, again, are a product of the data we have available. They're also very distinct from each other. They're distinct from Main Basin. And I'll say also that even though we have results at these specific sites in the subbasins, those results aren't necessarily generalizable to the whole subbasin because they aren't necessarily speaking for the whole volume there. And again, I'm going to filter this my trends at these sites to when and where hypoxic risk is the highest. So again, below a constant depth at each site. That does vary by site to maintain that consistency over time. And then I'm also focusing my early fall, late summer season is a window that I've just defined as August through November. So it's a 4-month time period. And then before I actually show real trends, I also want to talk about the actual properties at these sites. These are time series that I've wrangled all the data for my 5 sites, but I'm going to talk about Point Jefferson and Lynch Cove just for a second. These are conservative temperature, absolute salinity, and dissolved oxygen time series for both of the sites. And what we see is that at depth, Point Jefferson tends to be maybe a little bit warmer in the time series. At depth, it's also Point Jefferson has higher salinity. Lynch Cove is a little bit fresher. And then maybe most importantly of these time series, Lynch Cove in blue has much lower dissolved oxygen during fall at depth at this site. And so what that's showing is that there's definitely some difference between the mechanisms that control the oxygen at both of these sites. And that'll be something that is certainly interesting in further research and throughout this talk. Okay, so I have these time series. I'm at Point Jefferson now again. And this is my dissolved oxygen time series. I'm calling this a filtered DO time series because I have to, make these points make sense and also be usable in a trend analysis sense. I won't go into all the detail as to all of that, but know that these are per cast. So each of these points represent a single cast. They're also at the deepest portion of Point Jefferson, and they occur between August and November. So I have this time series. I want to know what the trend over time is. And so what I've done is I've used a thiol-sen slope analysis with a 95% confidence. That allows me to fit a trend line to this time series. In this case, at Point Jefferson, we see a decreasing oxygen trend of negative 0.27 milligrams per liter per century. I also have a 95% confidence interval from this analysis. And because that 95% confidence interval is different than 0, I can say that I have a statistically significant negative slope at this location. And so now I will show you the results that come out of that trend analysis for all the sites. But first, a reminder to take a water break. Thank you. Thank you all. Okay. So main basin sites, I'm going to start with main basin and their trends, and I'm going to introduce temperature, salinity, and dissolved oxygen separately. And so at main basin, Point Jefferson and near Seattle, I've labeled the sites on the x-axis of this plot, and then on the y-axis, I have the slope of the trend line in units of degrees Celsius per century. And so what we see here is that these sites in main basin are getting warmer, about 1.5 degrees Celsius per century degrees Celsius per century. And that's not necessarily good news, but that does mean that I'm probably doing my data analysis correctly because this is very similar to results that we're seeing in the Strait of Georgia, and which is nearby and would, potentially have similar warming trends. The next plot I'm showing is salinity. And so I'm showing Point Jefferson and near Seattle again, and then the trend in units of practical salinity units per century. And what we're seeing is that at both of these sites, there is an increasing signal, but only one of the sites is statistically significant. Although again, both indicate increasing salinity at depth during the fall. This next plot is kind of maybe one that we care a lot about, and that is trends of dissolved oxygen in units of milligrams per liter per century. And in this case, what we're seeing is both sites are decreasing. We're losing oxygen over the course of 100 years. And that value is between 0.27 and 1 milligram per liter per century. So it's not a super fast rate, but we are seeing evidence that exists. And that I kind of want to remind everyone that if we think back to the time series of oxygen at main basin, at Point Jefferson versus Lynch Cove, Main Basin does have high ambient oxygen and doesn't experience hypoxia, especially at Point Jefferson and near Seattle. So the oxygen here is higher than would be, potentially at risk given the slow rate of change and the existing ambient oxygen conditions. So there is a decreasing trend here, but it doesn't necessarily indicate a imminent risk of hypoxia at these sites. However, as my colleague Aurora will talk about in just a short amount of time, the ambient oxygen concentration of inflowing water into terminal inlets might have an impact on the development of hypoxia in those areas. So now I've added in the trend analysis for all of the subbasins, so the blue sites that are subbasins. And what we see is that for temperature, it's kind of a ubiquitous temperature trend that there is an increasing, it's getting warmer in all 5 sites that we've identified in Puget Sound. Some sites may be a little bit different than each other, but between 1 and 2 degrees Celsius per century. For salinity, not all trends are statistically significant, but all are indicating increasing salinity at depth during the fall. And then for dissolved oxygen, it's, maybe it looks a little different. They're not all the same. And what this is it's an interesting question of what is going on here. But what we're seeing is that in Main Basin, again, we have this decreasing signal. But in the subbasins, there isn't necessarily that same clear signal. At Carr Inlet, we do have a statistically significant trend, though there's more variability there. Saratoga Passage, which is this middle dot, is riding 0, and then Lynch Cove seems to have a slightly positive trend, although again, it's not statistically significant in that sense. Pointing out that Lynch Cove is the only one of these 5 sites that has hypoxia. So this is an interesting result and certainly merits further investigation as to the mechanisms controlling that trend and also oxygen in Lynch Cove. So I've talked about this first question, and now I'm going to discuss what mechanisms might explain these trends. And so this is also a part of the conversation that's limited by data availability. So over the last century, it's hard to have as the data resolution that you want to really answer these mechanistic questions, but we're going to do the best we can with what we have, and also I think we've come to some good conclusions here. So the first question within this is what mechanisms drive Puget Sound site warming? So the sites that we've identified in Puget Sound, they're all getting warmer. And what mechanisms might be causing that? And maybe the results of this might be somewhat obvious, but there are 2 important mechanisms to consider when we discuss what might impact temperature at these sites. And the first is that warm water warm water that's warm or anomalously warm from offshore can enter into Puget Sound via exchange flow from the Pacific. But water can also warm up while it's in Puget Sound, so the impact of local temperature or local atmospheric temperature is also important. And so I'll kind of get through this time series and plot on the right in some detail, but basically what this is saying, this is on the left, we have a time series of SeaTac air temperature, an annual average. So each of the point represents 1 year of SeaTac in the temperature. So the air temperature that we can kind of assume is maybe representative of the air temperature within Puget Sound, at least to some extent. The blue is Point Jefferson fall average surface temperature. So I'm looking at the top 5 meters there. And then in red is the deep temperature. So what I've already shown you trends for. And what we can see is this kind of an obvious plot, but that they are all kind of increasing and at similar rates, although not necessarily exactly the same, but it's getting warmer collectively. And then the plot on the right, I want to start with the first point here, labeled offshore. So this is a value that is reported in Whitney et al. 2007 at line P, station P4, which is pretty close to the Strait of Juan de Fuca. But this is a slope that's reported at that location. And then this, on the far right, we have the SeaTac air temperature. This is a trend over time. I've used the same LiveOcean slope analysis to identify this trend. It has a lot of variability. And then again, we have Point Jefferson fall trend, and then at both depth and at the surface in red and blue. And so what we see is that the surface in deep temperatures, so at Point Jefferson, the temperature in Puget Sound at that location kind of falls between the local and offshore temperature trends. And so what we can kind of surmise from this is that this indicates contributions from both remote and local processes. And so local atmospheric warming and offshore warming likely explain the warming in Puget Sound. Maybe, again, a bit of an obvious point, but things are getting warmer throughout the region. And the atmospheric temperature likely plays a role in warming that happens locally in Puget Sound. Now I'm going to move on to salinity trends. So these are the salinity trends that we've identified. Like temperature, salinity in Puget Sound can also be influenced by both remote and local processes. But given the data availability that we have, and then also the focus of this talk, I'm going to just talk about the influence of river flow on salinity here. So I bring up this diagram not to spend a whole lot of time on things that people likely already know. I feel like this room knows a lot about exchange flow. But for those who don't know what exchange flow is, it is a subtidal flow driven by a long channel salinity gradient and tidal energy, and tends to manifest or to be idealized as a salty bottom layer coming into the estuary, and then a fresh top layer going out. If we picture that this is Admiralty Sill in Main Basin, and then maybe some shallower terminal bays over here, we can kind of think of this as an idealized concept model of Puget Sound. So we have this persistent subtidal exchange flow. We also have river flow coming in because it's fresh water, it tends to sit at the surface. And the key takeaways that I want us to see here is that surface water can influence deep water via a process called reflux. So exchange flow, if it was an idealized sense, you'd have two clean layers flowing past each other, but that doesn't necessarily happen all the time, especially in areas where there's vertical mixing or enhanced vertical mixing due to sills or silvimetry. And so what you have is these instances where the fresh top layer going out can get mixed down into the incoming bottom layer. And so that process called reflux can essentially propagate surface signal variation throughout the estuary. And the other key takeaway is that this process happens on the resident, or we can expect that signal to manifest on the order of the residence time of the system, which in this case is approximately 150 days or months for the whole of Puget Sound. So knowing that, I'm going to take you to my attempt to explain the salinity trends that we see in Puget Sound. This top plot, I'm going to use the Skagit River to represent a typical Puget Sound hydrograph. Now, I'm not a hydrologist, but it is the largest river in Puget Sound and does represent somewhat of a typical cascade watershed properties. And so this top plot, I have in gray, the monthly Skagit discharge. And so we can see there's a lot of variability here. And then the other 4 lines are trend analyses. Again, I'm using the same LiveOcean slope analysis to understand how river flow has changed over time. So the black dotted line is the full trend. This is the full time series analysis for the whole 1940s on time series that we have at the Skagit River. And what we're seeing, and it echoed by other findings that other researchers have shown, is that there is not a statistically significant trend in flow overall. So what we think is that there's fairly constant flow at the Skagit River, and thus potentially for all the freshwater sources in Puget Sound. So that's not necessarily changing over time. The other 3 lines, I've made my seasons a little more complicated than they need to be, we've been considering August through November our fall, our late summer, early fall, where DO might be the lowest. And so I've subdivided the year into 3 seasons. So I have kind of my spring, which is April through July, and then December through March, which is my winter. And so these 3 trend lines on the top plot indicate trends that are just focusing on those seasons. And so during fall, we aren't seeing a statistically significant trend. So fall discharge isn't changing overall. But what we do see is that spring, in this gold line, spring flow is decreasing over time, while winter flow is increasing over time. And what that looks like potentially, or from the data, what we see, if we take a decadal average hydrograph, so if we say all the hydrographs that we have in the 1940s versus the 50s, et cetera, what we're seeing is that the lighter colors, which indicate earlier time series, or earlier average hydrographs, show more spring flow than currently exists. And so if you followed that this far, hopefully we all have, what this says is that spring flow, we're seeing a trend of spring flow reduction on the order of about 25% over the course of the century. If we take the residence time argument and assume that that change might manifest on the order of months, then we can start to understand that a spring flow reduction might impact the salinity that we see in the fall. And so the shifting flow might explain why we have increasing salinity, especially in places like Main Basin during the fall, if we have less flow in the spring. And finally, I've gotten to the last of my variables, and probably the one that we care the most about currently, which is what mechanisms influence dissolved oxygen trends. So I won't go into all the complexity of all the things that can control dissolved oxygen. But here we are investigating the effects of changing temperature and salinity on DO on a century scale. This is the data that we have over the last 100 years, and we want to see what mechanisms might explain these DO changes. And so if we all kind of like go back to, I guess not that basic, but some physics and chemistry that's pretty fundamental, we can recall Henry's gas law. And that is essentially what governs how much gas can dissolve into the surface layer of a liquid. And so for our purposes, dissolved oxygen saturation, so how much surface saturation can occur, how much oxygen we can have in the surface layer of water, is influenced by, or seawater, is influenced by temperature and also salinity, but to a way smaller extent. And so warmer temperatures, and also to a small extent, higher salinity, reduce dissolved oxygen surface saturation. So if we kind of do a calculation similar to an apparent oxygen utilization, but essentially we say, we know we're talking about deep fall water masses, but we're going to, pretend like they're at the surface and use calculations to allow us to do so. And then we are going to calculate the expected dissolved oxygen saturation from our observations at each of these locations. With these values, that we can calculate an expected trend that would be just based on saturation change, and then compare that to our observed trend. So this is what I've done. I've taken at each location for each cast, I've calculated an expected saturation for our deep fall water masses. And then I've compared that to the observed dissolved oxygen trend. So in this plot on the right, the filled red and blue circles are the trends I've showed you for DO over the last 100 years. And then the hollow golden circles are the expected trend if we were just considering saturation change. And so what we see is at Point Jefferson, that expected saturation trend explains the entire trend that we see at Point Jefferson that we observe. At locations like Saratoga Passage and Lynch Cove, the expected saturation trend is would indicate that we would have lower dissolved oxygen over time than we observe. And then at near Seattle and Lynch Cove, or sorry, at Carr Inlet and near Seattle, we see that the expected dissolved oxygen trend, this change in saturation, explains about 50% of that DO loss. And so this leads us to conclude that warming explains approximately 50% of the observed reduction in DO concentration over the last century. And this is kind of a big result. in particular, as we consider the impacts of climate change and how that might impact warming locally and offshore, and how that might impact dissolved oxygen in this very local, in our local estuary. This is also a finding that is not local only to Puget Sound. Work in the 2019 and 2020 in Chesapeake Bay also has very similar results to this, that they're seeing that warming explains approximately 50% of the loss that they observe in Chesapeake Bay. Okay, so I have come to my conclusion slide, and I will go over it fairly quickly, but mainly open it up to questions shortly. But I just want to rehash that over the last 100 years, we wanted to understand how DO is changing and why. And so we identified 5 sites with sufficient data for that century scale trend analysis. And so my first sub question of my science question was, do temperature, salinity, and DO show trends over time? And so during fall at depth, all the sites were warming. During fall at depth, salinity was generally increasing. And then during fall at depth, main basin DO was was found to be decreasing at a rate that was about less than 1 milligram per liter per century. And then the subbasins, Carr Inlet DO was decreasing, but Saratoga Passage and Lynch Cove actually don't show decreasing trends. And the mechanisms that we identified that might explain these trends are local atmospheric and offshore warming. And then also increasing salinity might be due to less river flow during spring. And finally, warming accounts for 50% or more of the DO loss if we consider saturation change over the last 100 years. So for the future work, I'm going to be publishing these results hopefully shortly in a paper that's going to go out soon, I think, I hope. And that doesn't close the case on all this analysis. The future work that we have to consider is, what about the other 50%? How can we account for what isn't accounted for by purely physical changes in temperature and salinity? And then also, the salinity piece is complex, and I've tried to identify some things that might impact that salinity change that we observe. But salinity change itself can impact exchange flow and local stratification and dissolved oxygen itself. And so how that whole picture shapes together is definitely warrants further research. And then also the sites are different from each other. And so that spatial variability is something that's also important to consider and investigate further. So I will leave it at that and say thank you and ask for any questions.
Thank you, Dakota. This is fabulous. And just want to highlight that particularly for those areas of future work, you all are doing modeling and monitoring or know some of these systems deeply well. And so feel free to make suggestions about how to think about that science moving forward. This is intended to be a collaborative space for that. To kick things off, feel free to raise your hand if you have questions. There were a few, Dakota, just kind of process-wise that I wanted to touch on first.
Sure.
One is just around the incorporation of tribes, kind of traditional observational data, and how that fits into kind of your existing data set and or any of the future research you're planning to do.
So sorry, one more time. You said that tribal.
Yep, tribal traditional knowledge or observations.
That's a great point. And so far we don't have any of that in this data set, but that would be something that I would absolutely welcome. And I think maybe my question is there more data? Should I be using more data? So that sounds like there is, and I would love to, that would be a great addition to this data set.
Wonderful, great. Tom Mumford, I'm gonna ask you to mute if you want to ask your question. Maybe. Tom, are you able to unmute?
There we go. Hi, Tom Mumford here. I'm pushing buttons here, but not getting very far. You touched on one of the really things that I've wondered about for a long time, and I think Parker and I have had this discussion. There's been a massive replumbing of Puget Sound, and the Skagit's an example of that. But those dams were put in the 1920s, just before these data sets. But you look at all the major rivers, and basically they've been drastically altered in the hydrographs. And what effect do you think that might have had that we could get at that would go back a little over 100 years? Skagit, Cedar, Nisqually, you just go down the list, and they've all been dammed for hydroelectric irrigation, so forth.
That's a great point. And yeah, you make that's the power of having data from that long ago and knowing, being able to track those system changes. But yes, I think that, yeah, certainly that would have an impact. I'm not entirely sure off the bat what impact that would have. It's actually the first time I've considered this question. So thank you so much for asking it. I'm, yeah, definitely intrigued in terms of, yeah, the seasonal variability that you would get obviously would be a significant change, given that, you have natural river flow versus dammed river flow. That's a really good question. And I think, do you know of data sets that, I guess, would include the pre-damming flow?
Well, the only data set, I'm a kelp guy, and
Okay.
we've got bull kelp data dating back to the 1870s, and we've seen losses prior to and fairly consistent over that whole period of time. So, but in terms of water quality, no.
Yeah, but I'd be interested to see. I mean, yes, if I feel like that would be a really cool thing to understand the impacts on your systems. And
yeah, one wonders if there are proxies in sediment cores.
yes, that's a good point. And I think that there has definitely been research in that area, although I'm not as familiar, but that's a great point.
Yeah. Thank you.
Thank you. Awesome
Thank
point.
you. David, I saw that you had a question in the chat and have your hand raised, so we'll go to you and then we'll come to Mike Brett.
Hello, what a great data set.
Thanks, Dave.
Quick question, given that there's lower river flow prior to these times when you see a drop in oxygen, could you say use the Knudsen relation and estimate the change in bottom water residence time, and for a given oxygen consumption rate, estimate how much a change in residence time would influence the other 50% of the loss of bottom water oxygen?
That is a great idea. And yes, I think I could do that. And I would love to try. Yeah, that's an interesting point. I haven't investigated specifically, yeah, the variation of residence time specifically over that century scale that might be impacted by river flow, or river flow changing and timing. So that's a good point.
Love those sort of collaborative ideas. Great.
Yes, love that.
Right.
I'm writing it all down.
Excuse me. Dakota, is great presentation.
Right.
I have a question for you about refluxing. We, discuss refluxing a lot, and I'm curious about how easy or difficult is it to actually quantify the magnitude of refluxing in Puget Sound, because the refluxing complicates things like, Knudsen exchange flow calculations get thrown off by that. So what are your thoughts on that?
That's a great point, and something that I am, learning about. I am taking a lot of my knowledge from Parker's 2021 paper, where they use box models and are able to really estimate residence time and quantify reflux in a sense. And so what I haven't gotten to the point of is, yeah, like quantifying like how much. Yeah, personally, I haven't done a lot of work with reflux and how that might be changing or how that might be varying and how that might change the Knudsen relation and how that can impact what we're seeing. But what I understand from the 2021 paper is that it's a tricky process to identify reflux and like how much that might be changing. I think especially in terms of if we consider like vertical mixing and how that modifies the amount of reflux that occurs. But yeah, that's a great question, Mike, and something that I should definitely look into more. Might require more modeling, and I'm not quite there, or not doing that quite yet.
Great. Well, and the beauty of all of this too, right? Great ideas can be things that you move forward, but that also others help to move forward in this as well.
Absolutely, yes.
Another question we had from Tanya is, do you anticipate the changing, slowing thermocline circulation trends to impact DO in the Puget Sound further?
And does that, like, are we referring to offshore thermocline circulation changes? Is that, am I understanding that question correctly?
Yes, Tanya says.
Okay, great. So I think that's been a big, I get this when I've shown this work before, the influence of what's going on offshore, and especially in terms of like ocean circulation change or Northeast Pacific change, how that might influence what's going on in Puget Sound. And so to maybe like, to maybe more walk you through what I've thought about with this, is that there is obviously changes happening offshore and like in the global ocean. And how those changes manifest in Puget Sound is, we've identified that there is variation in water properties with offshore fluctuations like Pacific Decadal Oscillation or El Nino. But what we've also identified is that because of the, it's a kind of a long pathway to get from the ocean through the Strait of Juan de Fuca, mix with the Strait of Georgia, and then get into Puget Sound. And then once in Puget Sound, there is a lot of modification that can occur in place. And so I think to, I guess, maybe not answer your question, I think the direction of change that might be expected from offshore circulation changes. We've already maybe identified that on the shelf that there is dissolved oxygen loss, but how that propagates into the system in Puget Sound, I so far have been unable to answer or, be able to, with observational data, draw that pathway to see how that might propagate into Puget Sound. But we can expect that, there might be some signal that might influence what we're seeing in Puget Sound. And then this is again where I say that I think, especially over the last 100 years of data analysis that I've done, some of these questions have come up, and then we've been like, I feel like we just don't necessarily have the data to answer that, these questions specifically. But modeling is where I think we'll be able to, that's the beauty of modeling, is that we can try to simulate how these might work, how that might impact what's happening. That's a great question. So thank you, Tanya.
Wonderful. Aiden, I see your hand if you want to go.
Yeah, thanks. I'm really curious about those changes in salinity that you observed, and I'm curious if you have any idea about where those are coming from.
Yeah, I think certainly the changes in salinity are, we're presenting this as this might explain part of what we're seeing. This change in river flow timing is what we have analyzed and thought has a lot of merit in terms of explaining. So kind of to go back over that, I mentioned that while the Skagit, or taking the Skagit as representative of a lot of rivers in Puget Sound, that really the flow over time isn't changing as a whole. Like we're not like, it's not just, there's not less water entering the system over time as a whole, but what we're seeing is a shift in the timing of when not heavy flow, but when flow occurs. And so what we're observing is that spring flow is decreasing as compared to winter flow. And so that the reduction of freshwater inflow in the spring may manifest in an increasing salinity during the fall, given the residence time of Puget Sound and the ability for freshwater signals to propagate through the system. Does that answer your question, sort of?
Yeah, thank you.
Yeah, of course. Thanks for the question. Appreciate that.
Great. So I'm going to wrap us with one more question so that we can also get to Aurora's. But feel free to also follow up in the chat, Dakota, on some of these. I think this is kind of a two-parter, which gets at what's available data-wise, which is one, whether or not your analysis included some of the orca buoys in particular. And then two, kind of the availability of data around chlorophyll and or nutrients, particularly with a lens to understanding these sorts of long-term trends and the role of respiration.
So that's two good questions. For this analysis, I didn't include orca buoys. mainly because they are so highly resolved compared to my, hopefully once every season or twice a season century scale shipboard profiling results. Now, that is not necessarily, I certainly would love to look more into the orca buoy. I know there's a lot of work going on there and a lot of valuable stuff, but they tend to be higher, like super highly resolved in more modern times. So they really didn't lend toward the century scale analysis I was trying to do. Very valuable data, and I would love to dig in. On your other question regarding data and about nutrients and chlorophyll. So I definitely tried with what we had available in the data that we have. And so, yes, there was collection of, there has been historical collection of chlorophyll or nitrate or other types of nutrients. But broadly, what we found is that was very constrained, and it was constrained in terms of its temporal resolution. So we weren't able to get like century scale trends out of it. I didn't include the trend analysis I did for that in my backup slides, which I now regret. But essentially, we weren't able to have meaningful century scale trends with the data that I currently have. That being said, if you have 100 years-ish, a couple decades of chlorophyll data, so basically before the 80s, if that exists and I don't know about it, that would be lovely to have. So let me know. Okay.
Wonderful. Mike, is your comment in regards to that before we transition to
Yeah,
Aurora?
it is. So that was really interesting what you said about the buoy data. And I understand your point that if you included the buoy data, it would kind of just swamp everything else out because you have, observations at a daily scale, whereas everything else is at most once a month. But could you take the buoy data and just average them at a monthly interval and include them that way so that they don't like swamp out all the other data so that, your analysis just doesn't become, buoy data analysis?
Yeah, you're definitely could do that, Mike, and actually probably just should. I think it was mainly that we were, with all of the monitoring data that we had, where we had sites that had century scale resolution, there wasn't necessarily like an orca buoy that was like right there. And I think Lynch Cove might be that exception, and that would be helpful to have. And so I should definitely add that in, but I think, I could certainly do averaging and make sure that it wasn't, over biasing present time results. But again, for the purposes of like the 5 sites that I was able to select that had century scale resolution, the orca buoys didn't necessarily add any additional information to those. But you're right, I should look at it and I should do it.
Thank you.
Mm-hmm.
Well, thank you very much, Dakota. Great insights and lots of possibilities moving forward. Hopefully that feels energizing and not totally overwhelming.
No, definitely. I appreciate it.
Good. With that, let's transition over to Aurora. And we'll move from the world of monitoring to the world of modeling.
All right, just to verify, can everyone see my screen?
Yep.
All right, perfect. All right. Thanks everyone for being here today. Really appreciate it. And I'd also like to thank all of my co-authors before we get started here who have really helped make all of this work possible. So today I'd like to present on our research studying how weak low oxygen exchange flow drives hypoxia in Puget Sound's inlets. And I always like to start my talks off with this satellite image of a phytoplankton bloom in Hood Canal. So you can see the phytoplankton as sort of this milky greenish hue in the water. And I think this image just acts as a nice reminder that what we're doing with models is trying to truly understand what's going on in a real world location that matters to us locally. So to kick things off, I want to lead with the main question that we're trying to answer in this work, which is what are the dominant processes influencing hypoxia in Puget Sound? A brief note on nomenclature here. I'm going to refer to dissolved oxygen as DO throughout this talk, and I'm using a hypoxia threshold of DO less than 2 milligrams per liter. So this question that we're interested in answering is a challenging question to answer because oxygen concentrations are highly dynamic and complex in Puget Sound. Hypoxia in prior modeling simulations has developed even without any land-based loads, suggesting that there are natural processes that are contributing to hypoxia. And so there's a lot more that we need to understand in terms of those oxygen dynamics. In addition, more than 90% of the nutrients entering the Salish Sea come from the ocean. Oxygen concentrations also vary spatially and temporally throughout the entire region, making it very difficult to just focus at a single point or a single time to understand the entire picture of what's going on. And so to really get a full idea of everything that's happening, we would need either a ton of observations everywhere at tons of times, which we simply just don't have enough of to complete this entire picture of oxygen, which necessitates the use of numerical models. Numerical models also provide an added benefit that we could use them to make predictions for how oxygen could change under different scenarios in the future. As a quick teaser of the results we're finding, we found that the exchange flow of different inlets is an important underlying process in establishing DO concentrations in these inlets. And so what I'm getting at here is that we're interested in this work currently in understanding processes. And by understanding these underlying mechanisms and processes relating to oxygen dynamics, that helps us give us a better idea of how we can mitigate related issues in the future. So today I'll start by talking about the methods that I'm using to conduct this analysis, and then I'll discuss my results in 3 different parts. First being a description of when and where the model is predicting low oxygen to occur in Puget Sound. Second, I'll present results on what our oxygen budgets are saying in multiple different terminal inlets in Puget Sound. And lastly, I'll sum up what we have identified to be the dominant factors influencing oxygen in Puget Sound's terminal inlets. And I'll wrap all of that up in a conclusion at the end. So to start, once again, this is a numerical modeling study. We're looking at hindcast data from simulation years of 2014 through 2019. And we're using the LiveOcean model, which is a model that's developed and maintained by Parker McCrady's group here at UW. LiveOcean is built using the Regional Ocean Modeling System, or ROMS, which is different than Salish Sea model, which uses FVCOM. It's also coupled to a nutrients, phytoplankton, zooplankton, detritus, plus oxygen biogeochemistry module, where detritus is dead organic matter. We initialized the model in October of 2012, and we treat the entire year of 2013 as a spin-up year, and we don't begin to analyze data until 2014 onwards. This map here is a map of bathymetry in the model in the entire domain. But what we're focused on for this study is just Puget Sound, which is denoted by the white rectangle on the map. I've added a few more details here about other modeling methods, but I'm just going to gloss over this. But if you'd like to come back and refer to this in the slides later on, you're welcome to do so. So in the model, we have a multitude of different land-based loads going into the water. So we have contributions from both rivers as well as point sources, which are largely wastewater treatment plants. A large portion of these data come from the Washington State Department of Ecology, and those data are also informing inputs into the Salish Sea model as well. So these ecology data provide us information about the location of many of these sources, as well as flow rates, nutrient profiles, temperature, etc. The ecology data spans from 1999 through about halfway through 2017 currently. And because our simulation extends beyond 2017, what we've done for all of these smaller rivers and treatment plants that we're using for with the ecology data for is we've developed climatologies to use as inputs to the model instead. So I'm going to show you an example of a climatology for Union River, which is located at the very head of Hood Canal. So in the rightmost panel, in panel A, this is a time series of Union River, and all of the thin colored lines are individual flow rates in Union River from the ecology data. And we've developed an annual average climatology, which is the thick black line. And we're using similar climatologies for many of the tiny rivers and all of the treatment plants and all of the associated state variables like flow rate, temperature, and nutrient concentrations for those sources for all of the years. However, LiveOcean also has many larger rivers where we're not using climatologies, but we're still incorporating interannual variability. So for instance, we have the Skagit River, and that's in panel B, and I'm just showing you 3 years here, just so you can, it's not too cluttered with all 6 years, but you can see that the flow rate for Skagit River does change and does have interannual variability. So we're still capturing that in our simulation. One more quick note on data processing. So LiveOcean outputs data and an hourly time step. So we take this raw hourly data, and at some point in our data processing, we always pass it through a 71-hour low-pass Godin filter. And we end up with these tidally averaged daily values for variables such as oxygen concentrations. And we're using these tidally averaged daily values to make all of the data products that you're going to be seeing in this talk. And I'm highlighting this because these tidally averaged daily values may be a little bit different than what you're used to seeing from some of the Salish Sea model products, which often look at the daily minimum oxygen concentrations rather than a daily average. The reason why we're using tidally averaged daily values for this work is because they give us a good representative understanding of the daily state of the system, which is useful for understanding the underlying processes and factors influencing oxygen, which is what we're after in this current body of work. And lastly, before I dive into the actual results we're seeing from the model, I want to give you a quick taste of what our model evaluation looks like. And these model evaluation results are just for 2017 because this is a year that we look into and analyze closely in our work. So here I'm highlighting some observation stations in terminal inlets in Puget Sound, so the ends of these branching bits of Puget Sound, and those are highlighted in pink. And then we're comparing that to the performance of the model in main basin stations and some of those stations in Admiralty Inlet as well. All of the observational data that I'm comparing the model to in this figure come from Ecology CTD cast stations. So all of the scatter plots that you're seeing here are property plots. So we're looking at a model value taken at the exact same time, location, and depth as an observation. We have these scatter plots for conservative temperature, absolute salinity, chlorophyll, and DO concentration. The diagonal line is a one-to-one line. And so ideally, if the model perfectly matched observations, all of those points would collapse to the line. In general, we're seeing that the model tends to have a bit more scatter in the performance in terminal inlets relative to main basin. However, the bias in the model performance is generally similar in both terminal inlets as well as main basin stations. If we focus specifically on DO, in general, LiveOcean is under-predicting DO with the bias of -1 milligram per liter. But I do want to emphasize that there is ongoing work in our group led by our postdoc Jillian Shong to improve the biogeochemistry module, and some of her initial results have shown improvements to that. But for now, we're still using this older version of LiveOcean in this work. But I want to emphasize that because the bias in DO is similar in all of the inlets, kind of everywhere in Puget Sound, and what we're interested in this work is understanding differences between different inlets, then this similar bias is unlikely to influence those relative differences as we're comparing the inlets. So it's still reasonable to be using the model to analyze and produce the results that we're producing, and I'm going to be sharing in this talk. And with that, I'll move into the first part of the results, which is the description of when and where the model is predicting low oxygen and hypoxia in Puget Sound. And we'll start by looking at when we're seeing hypoxia. This panel on the right is showing you a time series of hypoxic volume in Puget Sound over the course of 1 year, where every line here is representing a different year in our simulation, and the dashed black line is the median. Hypoxic volume is integrated over the entire region that's being highlighted in panel A. And just a quick note, we have omitted the straits in our calculation just because they may have different dynamics than the inlets in the sound. What we find is that, well, quick comment on the axes first. So the y-axis on the left in panel B is hypoxic volume in units of cubic kilometers. And then the y-axis on the right is the corresponding percent of the regional volume. And although there is interannual variability between the years in terms of the amount of hypoxic volume developing, we are finding that the maximum peak in hypoxic volume is occurring at relatively the similar time of year in all of these different years between the beginning of October through the end of September. So in this work, we're looking at the beginning of August to the end of September as being this hypoxic season where we expect oxygen concentrations to be lowest in the model. I also want to note that 2017, which is emphasized as a bold black line on this figure, has a hypoxic volume profile that most closely matches the median value line. And so we're treating 2017 as a good representation of what a median hypoxic year looked like. So this is the year I'm going to analyze more deeply in the coming slides, and just know that it's not overly hypoxic or a more well oxygenated year, but it's a good representation of a median year. We can also look at where hypoxia and low oxygen is occurring in the model. And for this, I'm showing you just results for 2017. And again, these data products are based on tidally averaged daily values of oxygen concentrations. So in panel A, this is a map of the number of days per year in 2017 in which the bottom vertical layer of the model has developed hypoxia. So any day where you are anywhere in the map where you see gray, that means that that location never developed hypoxia in the bottom waters. And anywhere that you see color means that there is at least one day in 2017 where that bottom water became hypoxic. We've identified that hypoxia is occurring in 6 different terminal inlets in Penn Cove, Port Susan, Holmes Harbor, Daybob Bay, Lynch Cove, and Case Inlet. In panel B on the right, this is a map of, again, we're looking at just the bottom vertical layer of the model, but now we're looking at the average DO concentration of that bottom vertical layer during our hypoxic season from the beginning of August through the end of September. And what we see in this map is that although these terminal inlets are the locations where we see the lowest dissolved oxygen concentrations, terminal inlets are also locations where we're seeing high oxygen concentrations as well. And so to answer our big question of what are the dominant factors influencing hypoxia in Puget Sound, we need to be able to understand the characteristics which differentiate the hypoxic inlets from the oxygenated ones. And so to answer that question, we've developed an oxygen budget in a bunch of different terminal inlets. But before I dive into the details of our oxygen budget, I just want to revisit our main question and the hypotheses that we're asking to try and answer this question. So our main question, as a reminder, is what are the dominant factors influencing hypoxia in Puget Sound? And to answer that question, I've been relying on this hypoxia framework, which is this nice conceptual model that was explained in Fennell and Testa 2019, which is a great review paper about hypoxia in coastal and estuarine systems. This hypoxia framework does a nice job of illustrating what our 3 hypotheses are that we're testing to answer our main question. So to orient you to this figure, on the y-axis is DO concentration of a system, and on the x-axis is time. And so all of the 3 lines each represents one of our hypotheses, and it is essentially telling us a story of how oxygen in a system is changing over time. Our first hypothesis and the first potential factor influencing oxygen concentrations is what I'll refer to as the low initial DO factor or DO naught factor. And this is a case where the initial DO concentration of a system is very low. And so even if oxygen is not being depleted quickly, it may not take much time for water in that system to become hypoxic because it's starting at a low DO concentration to begin with. An example of this is Oregon continental shelf, where oxygen depleted upwelled waters could cause the system to reach hypoxia sooner. The second factor that we're testing is what I'm calling the drawdown factor, which is related to a high biological drawdown rate. So this is illustrated on this figure by a line that has a significantly larger slope compared to the other lines. So this can be interpreted as oxygen being consumed much more quickly compared to other systems. Even if a system were to have a high initial DO concentration, because oxygen is being depleted so quickly, the system could still reach a hypoxic state. Example of this include the Baltic Sea, where the DO consumption rate has been increasing over the last several decades, and then the Oregon continental shelf again, where productivity has been stimulated by some nutrient-rich upwelled waters that are coming onto the shelf. And the last hypothesis that we're testing is the long flushing time factor, or T-flush factor for flushing time. And this is a situation where even if DO concentrations of the system are originally high, or if oxygen drawdown is not too fast, water resides in the system for so long that eventually all of the oxygen gets depleted anyways. And an example of this is, again, going back to the Baltic Sea, where residence times of 30+ years have been recorded. And so we're applying this hypoxia framework and all these different hypotheses to assess what is going on in Puget Sound's terminal inlets. And to answer this question, we're focusing on an annual scale. So we're thinking about initial DO concentrations being established during the spring in these Puget Sound terminal inlets, and then the lowest DO concentrations occurring during the late summer, early fall period. In the literature, scientists have hypothesized a combination of all of these factors might play a role. The drawdown factor has been hypothesized in places like Hood Canal and South Sound, which have symptoms related to high drawdown, such as high chlorophyll concentrations or low surface nutrients. The initial DO factor has also been proposed in places like Hood Canal, where low DO dense water intrusions may come in and establish some low initial DO conditions that could cause the system to reach hypoxia sooner in the year. And the flushing time factor has also been hypothesized in many of the weakly flushed and long residence time inlets in Puget Sound, which may be more susceptible to hypoxia. And we want to understand which of these factors is the most dominant in establishing DO concentrations in Puget Sound's inlets, or which combination of factors. And again, because we're seeing these extreme high and extreme low DO concentrations in terminal inlets, we're focusing our analysis on these inlets, and just for the year 2017, which is, again, behaves most like a median hypoxic year. We've analyzed 21 different inlets across Puget Sound, and I've colored and labeled all of them on this map here. And again, this analysis is based on tidally averaged daily values. But we focused our analysis only on 13 inlets that have a mean depth deeper than 10 meters. And we do this because the deeper inlets are likely to have slightly different dynamics than the shallower ones. Compared to the shallower ones, they're likely not as well flushed. There's going to be less bottom water in the photic zone, and they're likely also less well mixed. Of these 13 deep inlets, 7 of them are oxygenated, and they're colored in gray on this map. And 6 of them are hypoxic, and these are colored in pink. And these are the same hypoxic inlets that I had mentioned on one of the earlier slides. And lastly, before I dive into how we're constructing our oxygen budgets, just a brief reminder of the exchange flow. Dakota's already done a nice job of refreshing our memory on this, but I just want to emphasize that classically, the exchange flow is driven by a density gradient due to freshwater inflow, often coming from a river, and compared to salty, dense water coming in from the ocean. And that's driving what this exchange flow is. So let's move into how we're establishing our oxygen budgets. So in every single terminal inlet in Puget Sound, we have developed a 2-layer oxygen budget for the year 2017. And you could think of this as a 2-layer box model in effect for every inlet. We're studying how oxygen changes in both a surface layer as well as a deep layer. And these oxygen budget equations are written out on the screen here. The left-hand side of both equations is how the total integrated amount of oxygen contained within a layer of the inlet is changing with time. And that is described by all of the terms on the right-hand side of the equation. The first term is the exchange flow contribution of oxygen to the equations. So we're assuming that all of the inflow is coming into the deep layer and the surface layer is exporting oxygen. And we're calculating this using the total exchange flow, or TEF method. The surface layer also has an air-sea gas exchange term, and we also have a source of oxygen due to river inflow. Both layers also have an assortment of different biological processes, but in the surface layer, this is predominantly a source of oxygen due to photosynthesis, and in the deep layer, this is predominantly a sink of oxygen due to consumption. And lastly, we take the difference between the left-hand side of the equation and all of these terms on the right-hand side of the equation, and we ascribe that difference to be the vertical transport between the surface and the deep layer. Because the lowest DO concentrations tend to occur in deeper waters, we focus our analysis just on the deep layer of all of the inlets. And I've defined this term DO deep, which is in effect the mean DO concentration of an entire deep layer of an inlet. Another simplification you'll see me make later on in some of the figures is that I have combined all of the physical terms in the budget to be one single term called the exchange flow and vertical transport. And I've combined all of the biological terms to be a single term called photosynthesis and consumption. So that's a lot going on in our budgets. And so before showing you the full conglomerate of results, I just want to walk through an example of what an oxygen budget looks like for just a single inlet. And for that, let's focus on Lynch Cove. So this figure is a time series of all of the different terms in the deep layer oxygen budget equation for Lynch Cove. The y-axis is DO transport in units of kilomoles of oxygen per second. And the reason why this is in units of kilomoles is because we're looking again at this total volume integrated amount of oxygen rather than a concentration. And we're looking at how this is changing with time, which is on the x-axis. The black line in this figure is this net effect, this net change of oxygen in Lynch Cove due to all of these other different processes. We have the exchange flow in dark blue, which is a large source of oxygen to the deep layer, nearly balanced by vertical transport in light blue. We have photosynthesis in dark red, which is another source of oxygen, and then consumption in light pink, which is a sink. What we're interested in most for these budgets is what processes are establishing the lowest DO concentrations in the late summer and early fall, this high impact period, something that Dakota also focused on in her talk. And so to understand what's going on in establishing those late summer, early fall oxygen concentrations, we want to focus on the months that are just preceding that period. And so we're looking at what's called a drawdown period, or what I've defined to be a drawdown period, which spans from mid-June to mid-August. And we've looked at oxygen profiles in all of the different inlets that we're studying, and we've verified that oxygen is decreasing in all of the inlets during this period. So we can simplify our budget analysis by zooming into just this drawdown period and calculating an average of every single value in the budget equations. So instead of getting all of this variability we see in the time series for the exchange flow term, for instance, we can replace that with a single average value during the drawdown period. So then we can simplify this time series into a bar chart. So this is a bar chart for Lynch Cove still, and this is the same colors and the same variables that were just on the previous slide. A quick note about a change in the y-axis scale, however, we now have oxygen change in units of milligrams per liter every day. And the reason why we now have a concentration here per day is because we've now volume averaged all of the budget terms by the volume of the deep layer of the inlet. And we do this in all of our analyses because we don't want large inlets with a large volume to have a large bias compared to smaller inlets. And so now in this bar chart, we can see on average how all of these terms are influencing oxygen during the drawdown period in Lynch Cove. And on average in Lynch Cove's deep layer between mid-June to mid-August, we see that oxygen is decreasing at a rate of minus 0.028 milligrams per liter per day. And this is the sum of all of these other terms that I had mentioned earlier. I've built the exact same bar charts for every single inlet, and I've combined them all into a single bar chart, which I want to show you here, which is the results that we can use to test our first factor. So in the first panel, this is, again, the exact same variables, exact same type of bar chart that we just saw for Lynch Cove on the previous slide. But now what I've done is I've grouped all 7 of our oxygenated inlets into the hatched bars. And so these are an average value of all of the oxygenated inlets. And we have the average of all hypoxic inlets in the solid bars. What I want to emphasize with this top figure is that in all inlets, the exchange flow is the largest source of oxygen to the system. And this is going to come back later on, so I just want to highlight that now. But for now, to zoom in and get a better sense on the net decrease and the net effect of physical and biological processes, I've combined the exchange flow and vertical transport and photosynthesis and consumption terms in the bottom panel to see what's going on. And in general, physical processes are a net source of oxygen. Biological processes are a net sink of oxygen in both hypoxic and oxygenated inlets. And the net effect of which are the black bars, where we're seeing that both hypoxic and oxygenated inlets are losing oxygen at a very, very similar rate. And when we conduct a statistical test, we cannot say that these are different. And so this tells us that oxygen is decreasing at a similar rate in both hypoxic and oxygenated inlets, which means that a difference in their rate of oxygen consumption or oxygen decrease is not what's differentiating between the two types of inlets, which tells us that it's not the drawdown factor that's driving hypoxia in the hypoxic inlets. In fact, we find that DO is decreasing at the same rate in almost all inlets except for Debab Bay. These are box plots of daily net decrease rates of DO in all of the different inlets during the period from mid-June to mid-August. I've ordered the inlets on the x-axis from the shallowest to the deepest, and the y-axis is that net decrease term in units of milligrams per liter per day. And although there is a ton of variability, we find that the mean value, the mean decrease rate of all inlets indicated by the navy dots is pretty much the same. The mean value of all inlets is the blue line, and everything kind of lines up there except for Debab Bay. So again, just to emphasize, DO seems to be decreasing at a similar rate in all of these different terminal inlets in Puget Sound, whether they be hypoxic or oxygenated in late summer, early fall. So something else must be a dominant factor in establishing the DO concentrations in these terminal inlets. And with that, I'll move into the last part of my results, which is identifying what these dominant factors truly are. And I want to go back to a point I made earlier, just a brief reminder that the largest source of oxygen to these terminal inlets was coming from the exchange flow, and we saw that in the bar charts earlier. So as we're thinking about one of the other factors, our initial DO factor, it's likely that the exchange flow is what is establishing those initial DO concentrations in these inlets because it is the largest source of oxygen. So here is a scatter plot of monthly mean DO concentrations in the 13 different terminal inlets. So that means that there's 12 times 13 points on this figure. On the y-axis is the monthly mean DO deep concentrations of the inlets, which again is the mean deep layer DO concentration of the inlet. And on the x-axis is the monthly mean DO in concentration, which again is the DO concentration associated with the inflowing branch of the exchange flow. The diagonal line is unity. And what we observe is that there is a strong correlation between DO deep and DO in. And in fact, especially for the more oxygenated inlets, many of these inlets have DO deep equal to DO in. And so this suggests to us that DO in is a very important factor in influencing DO deep of the inlets. And thus, that tells us that the initial DO factor is important to establishing the deep layer DO concentrations of an inlet. But this doesn't tell us the whole story. We see that there is a lot of points in which DO deep of the inlet is lower than DO in. And we can get a better idea of what's going on if I now color these points by the monthly mean flushing time of the inlet. We're defining flushing time of the inlet, T flush, as the volume of the inlet divided by the inflowing volumetric flow rate of the exchange flow. The darker the color means the longer the flushing time. And now what we see is that for these points where DO deep is lower than DO in, we're finding that they tend to have a longer flushing time. suggesting that longer flushing times allow more time for biological processes to consume oxygen in the inlet before that water is flushed out. So putting this all together, we're seeing that a combination of both the initial DO factor as well as the flushing time factor are important factors in establishing the DO concentrations of the deep layer of Puget Sound's terminal inlets. We can take this analysis a little bit further as well by looking at how these two different processes, how these two different factors influence the seasonal cycle of the deep layer of Puget Sound's inlets. And I'll do this by walking through two different example inlets. We have Crescent Bay, which is located in Whidbey Basin, and this is an oxygenated inlet. And we'll look at Lynch Cove again, which is a hypoxic inlet. I want to note that these scatter plots are the exact same scatter plots that I just showed on the previous slide. The only difference now is that I've slightly changed the flushing time scale just because the flushing times didn't reach the maximum value. And so it's a little bit easier to see the variation in color. And also, I'm only highlighting the points that are corresponding to the respective inlets, so either Crescent Bay or Lynch Cove. If we look at the first panel in Crescent Bay, we find that all of the points on every month of the year 2017, they all fall on a line of slope roughly equal to 1. And that suggests that, at least in Crescent Bay, excuse me, that the inflowing DO concentration of the exchange flow is primarily what explains the seasonal cycle of the deep layer DO concentrations in Crescent Bay. In Lynch Cove, however, we see that some of these points fall on a line of approximately slope 1, but many of these points deviate from that line of slope 1, especially ones that have a longer flushing time. And that suggests that a seasonal cycle in the flushing time may also have an influence on seasonal cycle of the DO deep concentrations in Lynch Cove. And we can explain this a little bit more clearly by looking at the same point, but just with a different plot. So I'm keeping the scatter plot of Lynch Cove there on the right, but now I'm bringing up a time series of Lynch Cove during 2017. So the black y-axis on the left is the DO deep concentration in Lynch Cove over the year 2017. And the blue y-axis on your right is the flushing time of Lynch Cove over the year 2017. And what we see is that there is this seasonal cycle in DO deep in Lynch Cove, which we see in all inlets, where DO is decreasing during the spring and reaches a minimum in late summer, early fall. But what's interesting is that we also see this seasonal cycle in flushing time as well, where the flushing time is changing throughout the entire year. And because the flushing time is again equal to the volume of the inlet, which is more or less constant, divided by the inflowing volumetric flow rate of the exchange flow, then what we're really seeing is a seasonal cycle in the flushing time. A quick note here on what these dots are on the time series. These dots are the monthly mean values for both DO deep and flushing time, and they correspond exactly to the points that are being shown on the scatter plot on the right. So when we step back and we take this all in, we're seeing that in an inlet like Lynch Cove, the DO deep concentrations and how they vary seasonally depend on both the combination of DO in as well as a seasonal cycle in the flushing time as well, which is a seasonal cycle in the exchange flow strength. So now let's summarize and synthesize all of the results we've seen so far. And for that, I'm going to rely on this hypoxia framework that I introduced earlier on. But what I've done is I've adjusted this hypoxia framework based on the information that we've learned about the factors leading to hypoxia in Puget Sound's terminal inlets. The first thing that I want to emphasize about this new modified figure is that the slope of all of the lines is the same, and that is to reflect our finding that oxygen is decreasing at a similar rate in all of the terminal inlets in Puget Sound. So again, we're finding that it's not the drawdown factor that is dominating what is differentiating between hypoxic inlets and oxygenated inlets. What we're finding is that there are two dominant factors that are influencing oxygen concentrations in Puget Sound's inlets. The first being the initial DO factor, and that's related to the DO concentrations of the inflowing branch of the exchange flow. And in some cases, if that inflowing DO concentration is low, then that will establish low initial DO concentrations in the inlet. and that's indicated by the solid line on the bottom of this figure on the left. The next one that has an important role in establishing DO concentrations in Puget Sound's inlets is the flushing time factor. And this is controlled by weak exchange flow in the terminal inlets. So even if the DO concentration flowing into the inlet is still high, if the exchange flow is really, really weak, then that means that the flushing time is long in that inlet, and that inlet may be more susceptible to hypoxia. We also have cases such as Lynch Cove, where we have a combination of both the flushing time factor and this initial DO factor, where we have a long flushing time and a low inflowing DO concentration. And that's denoted by the dashed line on the bottom. And this is sort of a worst case scenario where we're likely to see some of the lowest DO concentrations in the sound. The main point I want to emphasize with all of these findings are that the inflowing DO concentrations that are establishing the initial DO concentrations of the inlets are controlled by the DO concentrations of the exchange flow. And the flushing time is also controlled by the strength of the exchange flow. So the exchange flow plays an important role in establishing the DO concentrations in these terminal inlets in Puget Sound. And so we can summarize these findings very succinctly in what was the title of the talk, which is that weak, low oxygen exchange flow drives hypoxia in Puget Sound's inlets. We can summarize these results a little bit more. So deep DO in terminal inlets we're finding is not being driven by differences in local biogeochemical processes. The most hypoxic inlets in Puget Sound are not ones that act as isolated hotspots of high DO consumption or high DO depletion rates. Instead, deep DO concentrations in terminal inlets of Puget Sound are strongly influenced by what flows into the inlets and how long it takes to flush the inlet, both of which are attributed to the exchange flow of the inlet. These conclusions imply that the most effective management strategies for managing oxygen in these inlets may be ones that treat these hypoxic hotspots as the end members of a highly connected system. And I do want to highlight that this conclusion, this implication, is not novel, that this idea is consistent with ongoing efforts to consider Puget Sound oxygen more holistically, rather than treating these hypoxic hotspots as isolated bodies. However, there is a however here, that although terminal inlets are all influenced by the exchange flow, there are differences in what might be controlling the exchange flow in these terminal inlets, and there may still be differences in the underlying mechanisms in each of these terminal inlets that warrant further investigation. So there's still a lot of important considerations left in this work and whatever work follows it. One main question is, what is it that controls the strength of the exchange flow in each of the terminal inlets? Like I mentioned earlier, classically, estuarine circulation is controlled by a density gradient due to freshwater inflow from river flow compared to more salty water coming from the ocean. However, many of these terminal inlets don't even have a river or a large river at its head, suggesting that there must be some other mechanism that's influencing the exchange flow in these inlets. Perhaps tidal pumping could play a dominant role, or perhaps something else entirely. And it's important to understand the mechanisms of the exchange flow because they play such an important role in establishing oxygen in these terminal inlets. So it's also important to understand what could possibly change the exchange flow. Some work that Kangakar and Yan 2023 has done sort of related to this idea of thinking is that freshwater discharge from wastewater outfalls could change the strength of the exchange flow. So those types of considerations are important to keep in mind as we move forward with research related in this field. Another important consideration are to understand the relative impact of different underlying processes, as well as their projected change in the future. So in particular, what is the contribution of land-based loads to Puget Sound's hypoxia compared to natural processes such as the exchange flow? We also want to understand how shifts in different mechanisms underlying what's controlling the exchange flow or other underlying processes may change in the future due to some changes like climate change. And so although we've made great headway in this research so far, there's still a lot of important considerations moving forward. With that, I just want to summarize and say thank you all for your time. Thank you for being here. I'm happy to start this conversation with all of you, and I'm excited to take any questions. Thanks.
Wonderful. Thank you so much, Aurora. And now that you all have kind of heard both content from Dakota and Aurora, we'll have questions. Feel free to kind of jump between both. But also want to say, if there are gaps that you all see in terms of research questions that around what's driving DO in Puget Sound, as Parker mentioned at the start, there is a wide range of researchers who are exploring this. So please feel free to put some of those ideas and suggestions into the chat or follow up over email with us as those percolate. So Aurora, to kick things off, we've got a question about inlet shape and bathymetry, and how you're accounting for that, in particular, the shape of the entrance. And does that seem to have a strong influence on T-flush and exchange flow parameters?
That is a great question. And we haven't looked at that explicitly yet in this work. The main thing that we've taken into account so far is just the volume of the inlet and the mean depth of the inlet. And in terms of any other geometric features, we haven't investigated too much. Certainly the shape is likely to play a role in some of those exchange flow processes, perhaps especially ones that might be related to exchange flow driven by kind of these geometric shapes, but it's not something that we've looked into yet. But I really appreciate this question because I think this is a great consideration as we begin to think about the mechanisms driving the exchange flow in the future.
Wonderful. Appreciate that. I was going to ask Steve to clarify his question about rationalizing conclusions, but I think he may have dropped off since he's in Europe, time zone wise. So we may follow up with him as needed. There's also a question about just explaining the changing severity of hypoxia in Lynch Cove, in particular in the last 20 to 30 year time period. So either Aurora or Dakota, if either of you want to speak to that.
I might like Dakota take this if she's comfortable with it, since I haven't looked at more than 6 years.
Yeah, I think I also have been looking at things on more of a century scale. So the last 20 or 30 years, I know that there is certainly documentation to suggest that Lynch Cove severity of hypoxia is increasing. We haven't really at this point gotten into the mechanisms that might drive that. Now, that is something that both Aurora and I and also others in our group are gearing up to maybe get toward, is explaining why, especially hotspots like Lynch Cove and also Penn Cove, which is something that we'll be working on more in the future. So yeah.
Wonderful. Appreciate that. In the theme of resources, just to highlight that there are some great ones being shared around seafloor mapping that might get to some of the bathymetry as well. Curious, feel free to drop questions into the chat or raise your hand if folks have other thoughts. Otherwise, Aurora, Dakota, from what you've kind of heard in questions, any requests you want to pose to the folks on the line? Yes, Stefano, go for it. You're muted.
Yeah. Thank you so much, guys. That was a fantastic presentation to see both of them. Aurora, I was just wondering whether I was really interested in the comparison when you dug into the details between Lynch Cove and one of the others to try to tease apart what's the driving forces there. And so the example you had was that Lynch Cove was this combined effect of the lower DO and also the flushing time. I'm just wondering if there was any others that you've looked at that are like that, considering how different the shape of it is and its position and so forth. And then I had a comment just on the geometry after that.
Sure, thanks for that question, Stefano. So I made similar plots for all of the inlets, and there was certainly a mix of inlets that look more similar to Crescent Bay, where everything kind of looked like it fell on a line of slope 1, and then things that looked more like Lynch Cove, where we see more of this kind of blob shape rather than a line. One that springs to mind is Daybob Bay, which is also located off of Hood Canal, where we have a combination of both low inflowing DO concentrations, albeit not as low as what's going into Lynch Cove, as well as a very, very long residence time. And it was sort of a similar blob shape off to the side here. I could share some of those figures with you for those other plots or other inlets later on. But yeah, there is certainly a kind of a spectrum of behavior, and these are kind of examples of what those extremes look like.
Yeah, that's really interesting to hear that Dabob Bay is the other, because it's really it's at the end of you know, this very fjord-like system compared to some of the others, and so I think that's interesting in itself. I think it would be very interesting to look at, as was mentioned earlier, some of the geometry, particularly with the cutoff that you're using for the mouth, and then consider the geometry just before that, and play around with that. It could be really, it could tease apart some of that classification even further.
Yeah, that's a great idea, a great thought. Thank you for that. Yeah, it's not something that we've explored yet, but it certainly seems like it could play a role. It would be important to look at.
Wonderful. Bob, go for it.
Hey, thank you, Aurora. That was great, and also Dakota, really interesting work. One thing that I was thinking about, you know, in these different terminal inlets, and a lot of times I think it gets overlooked, is the amount of secondary productivity that's going on. So I think in some of these terminal inlets where you have in more or less intact benthic community, particularly lots of shellfish beds, I think that, you know, you do have the buildup of phytoplankton bloom and then the decay, but if there is a functioning benthic component, the oxygen drawdown may be metered because it's now going into secondary productivity instead of just being remineralized in the water. Have you been looking at that aspect of you know, how that can affect, you know, biologically mediated is more than just the phytoplankton, but also you know, being consumed by the benthic community, and you know, that could also be a factor in why there's some differences in some of these areas. But very interesting. I also had a question on, you know, you were talking about how there's a bias among these different terminal inlets, and the bias is about the same. And if I understand that, it may be that in some areas, even though it has the same amount of bias, it may have a more profound effect in different areas than others because of it's closer to some kind of critical point or tripping point. Anyway, that I was thinking about that also. Thanks.
Yeah, thank you for your comments and your questions. You know, it's great to hear all these different perspectives of how to think about these questions that I haven't, you know, thought about them from yet. So to address your first point, in our model, we have both water column respiration as well as benthic remineralization as well. So we have particle burial that consumes all of the oxygen currently. And that's actually in some ways potentially related to your second point, where we're trying to understand bias in these DO measurements. And one of the things that our postdoc and our group has been looking at in particular is this particle burial rate, and that maybe that needs to be something that could be tuned. And so it is definitely possible that even though the bias is similar in all of these inlets now, that could change what we're seeing in terms of our final results. But it's something that definitely needs a little bit more work and more consideration as well as we're moving forward. And I do appreciate your point that, you know, the biological aspect is very complex, and it's certainly more complex and how I've simplified it as just a photosynthesis and a consumption term, but that there's a lot of processes that are going on.
Great, thank you.
Thank you, Bob. All right, with a few minutes left, Gordon, we'll have you be our final question to close things out.
Oh, geez, the pressure. Yeah, Aurora and Dakota, thank you a lot. Those are really well done and thoughtful presentations. Question for Aurora on kind of in the weeds of the modeling. I noticed when you had the plots of observed versus predicted, so the observed being the measured data. Oh, you're going to go back. Awesome. Yeah, so bottom left, there's essentially no relationship between the chlorophyll, the observed chlorophyll and the modeled chlorophyll there. What's the potential for that to kind of propagate through to your final conclusion that biogeochemistry is not really that important? Is there a issue there or not?
Yeah, thank you for your question. That's a very good observation. So what we're finding is that there seems to be, when we look at time series, I should say, of different observations compared to the model in surface chlorophyll in particular, we're seeing that the peaks in the observations don't line up with the peaks in the model. However, the annual average amount of chlorophyll is still similar between both. And so the model is not capturing all of these different distinct peaks very well. And that's likely due to the fact that there's only one phytoplankton species in the model versus an assortment of real different species that exist in the actual water that might be peaking at different times of year. But because DO is generally matching up in terms of when things are going up, when things are going down in both the observations and the model, we feel comfortable that we're seeing that this chlorophyll amount is similar when you average over the whole year between the model and the observations. That being said, I do want to emphasize that there is still room for improvement, and the model is not perfect, and it's definitely possible that those errors could still propagate into what we're seeing in DO and those final conclusions in ways that we haven't quite quantified yet. And we want to be mindful of that as well. So hopefully in future iterations of the model, we'll be able to see those improvements and hopefully build more confidence in the results that we're seeing. But yes, this is certainly something that we are aware of and we're trying to be mindful of and understand. So thank you for that question.
Thank you, Gordon. All right, so as we wrap up, just a reminder, we will put this recording and we will put these slides on the website and email them out to everybody for ease of access. Alex and Parker as advisors, anything you want to say in closing?
I can go quickly first, and then I'll let Parker have the last word. Mostly just to thank Aurora and Dakota. This was, I think, beautifully presented, and I'm really grateful for it. And they've acknowledged earlier on that this is kind of pulling together, 100 years of people's observations. And so obviously an enormous community of researchers trying to understand these questions. And so grateful for all of the contributions from everybody who is sort of building towards this and continues to add questions and ideas that can help us guide our future questions. Add, Parker?
Yeah, sure. I think can you hear me?
Yep.
Yeah. I am really pleased with how both of the students have worked out this research, and I'll just say that I think of these results from both Aurora and Dakota as really sort of new and groundbreaking and showing us things that were not part of the conversation about how we thought about Puget Sound before we started this research. It's not incremental. These are really big, important results that need to be, considered and tested by other people and thought about more carefully. So thanks again.
Wonderful. Well, thank you all. We appreciate the robust discussion today, the really thoughtful questions, shared resources, recommended next steps. As we mentioned at the start, we're excited to be kind of revamping this series. And so we will have more to come in the coming months, particularly around biological vulnerability with Tim Essington, looking at metabolic index, so temperature-dependent oxygen supply and demand. But if you have more thoughts and questions around water quality, DO, nutrients in the sound, please feel free to reach out.